This is ESE 471. My name is Neil Patwari. I'm going to talk about how we receive bits using an orthogonal basis. And recall the last video was about how to transmit bits using an orthogonal basis. That is that the transmitter picks one out of capital M possible symbols to send based on what bits it wants to send. And each one of those symbols is a linear combination of capital K waveforms. This video is about how a receiver decides what symbol and therefore what bits were sent. And the main problems are that the received signal has gone through a radio channel and thus has been attenuated, filtered, and had noise added to it. And we talked about the channel last time. We showed this diagram. For this video segment, we're going to ignore this linear filter because we'll get to that later. And we're also going to assume that the receiver, now we're kind of at the receiver here, that the receiver has a gain stage that undoes the effect of this attenuation. In fact, it multiplies by about the same amplitude that the channel reduces the signal by. And that amplitude then gets canceled out. Now, the noise gets multiplied by the same alpha that the signal is getting amplified by here. So we don't change the signal power to noise power ratio, that is the signal to noise ratio, or SNR. The SNR remains constant, but we are able to have a signal with about the same amplitude as the one we sent. So we're going to call this received signal RFT, and we're going to talk about what the receiver does with it. Okay, but the main problem again is now that this noise is added in. Okay, so the receiver must answer the question, what symbol SM was sent? And it's going to do this by figuring out which is closest to R of t. That is, this distance, R of t, minus SM of t, should be very small. And in fact, what do we mean by small in a time domain signal? Well, we're going to square the difference, integrate, and that is going to be our error. Okay, it's the energy between R of t and some symbol Sm of t. Okay, so our symbol that we want, we're going to call that m hat. M hat is going to be the index of our best guess for what symbol was sent. M hat is going to be the m that minimizes error. I could plug in different m's for this error formula, and I could get a different error. One of the symbols, m, is going to minimize this error, and that's the one that the receiver is going to pick. We're not going to justify why minimizing the squared error is the best thing to do at this point. We'll talk about why it's optimal later. Our motivation at the receiver is to find this symbol m hat that minimizes the error. Okay, we'll skip to the solution of solving this equation for this m hat. But what we're going to do is we're going to tell you what the solution is. And the solution is that we're going to find these values that are the inner product of R of t and the basis functions vk of t. This inner product is what we defined before, the integral of the product between R of t multiplied by vk of t. We're going to define this xk for k equals 0 to capital K minus 1. That's for each basis function that we have in our basis. And in fact, we're going to define a vector x to be these values, x0, x1, up to xk minus 1. This is our vector representation of what we received in the basis. And the solution for m hat is going to translate to a different arcmin, but it's going to be this difference between x and the vector representation of the symbol in the symbol space. Okay, and we can either minimize the squared distance between x and SM or the distance itself. It doesn't really matter. The distance is what you would think of in a vector space, this Euclidean distance, the square difference along every axis, every dimension, here every basis function, squared and summed. And if I wanted to write the distance, I could get rid of this square and take the square root of this whole sum. That's our Euclidean distance. Finally, once you find this m hat, we're going to look up what bits, and that's going to be our bits out. And once we decode the next symbol, we'll get a different m hat, and it will lead to more bits out, and so on, until we get to the end of our message. Okay, so let's do an example. And I'll follow up with the example that we did in the last video, which was m equals 4, k equals 2 modulation system. And I'll write down the spec for that modulation system. And let's draw what comes out of here. What would happen if I received this signal, r of t? And in this time period between 0 and t sub s, because of noise, I'm not going to receive exactly one of these symbols. I might receive something like this, okay? So our receiver is going to take this r of t and it's going to integrate and multiply, in our case between 0 and t sub s, because instead of minus infinity to plus infinity, our phi sub k, our phi sub 0 and phi sub 1 are only defined between 0 and t sub s. So I'll multiply phi of t, phi sub k of t with r of t, integrate. I'll do this as an integral here. It will also be called a correlator, and this will compute x0. And I'll do the same thing for x1. Now I have this vector x, because I have these two numbers, and I'm going to take that and I'm going to make a decision. This decision block is going to be finding the m such that this x minus sm is minimized. And out of that decision is going to come m hat, either 0, 1, 2, or 3. So let's say I get a particular value of x0 in this example of 0.1, and over here I get an x1 of minus 0.5. Okay? What I'm going to do to show this graphically is I'm going to plot these vectors s0, s1, s2, and s3, and the vector x. So I'll start with the values of s, and this was S0 was at 1, 1. Okay, so that's what I'm going to plot. And I'm going to draw this axis as phi 0, and this axis is phi 1. Okay, and you can see how S0 was 1, 1. I had this as phi 1 and phi 2 rather than phi 0 and phi 1. Forgive my mistake there. This symbol 0 is composed of 1 of phi 0 of t and 1 of phi 1 of t. And then you can see how I'm going to have my other symbols. My other symbols sometimes are labeled with a minus 1. So S1 here is going to be at minus 1, 1. S2 is going to be over here with a minus 1, minus 1. And S3 is going to be over here. Okay, great. So what I'm going to do is I'm going to plot x0, x1, 0.1 right over here, and minus 0.5 right over here. And I'm going to see that my vector x is right there, that red dot. And I'm going to ask which is this closest to. Well, because of the symmetry of these points and the axes, you can see that anything in this bottom right quadrant is going to be closest to S3 versus any of these other symbols. And anything in the top left quadrant is going to correspond to an m hat of 0. So just by drawing these, I don't have to compute the distance to every of the 4 symbols. I can see graphically that the m hat in this case is equal to 3. And then, based on whatever bit string I labeled S3 with, that would be the bits that my receiver has received.